Hi everyone. Today we will be discussing about BERT, which is an extension over transformers that we have already discussed in our previous videos. So let's first of all understand what is a basic difference between transformers and BERT, and what extra BERT is bringing into the transformer architecture. So let's understand. So first of all, in BERT, if you remember in transformers, we have this encoder and decoder part. In case of BERT, we only have the encoder part. The decoder has been eliminated. Also, the encoder is trained in such a way that it achieves bidirectional training, unlike transformers, which receives just unidirectional training. So I will discuss that later. What is the difference between a bidirectional training and a unidirectional training? The third one being the goal of BERT is to understand a particular language, right? But in case of transformers, we are training transformers for particular problems. Like if you wish to generate a question answer system, then you are training a separate transformer. If you wish to generate a speech to speech conversion or text to text conversion system, then you're generating a different transformer. But in case of BERT, what happens is that we have two parts. One is a pre-training part, and other is a fine-tuning part. So what actually we're trying to do is to make the model learn the language only, so that eventually in future, if we wish to change to some if we wish to do multiple tasks, we are not doing the core training again and again. So and we are just in the end we are just using transfer learning, tweaking out some last layers, so that the training part gets reduced heavily and we can perform multiple tasks using the same model. And the fourth one being the tokenizer being used is word piece. So I will discuss word piece in some of my later videos. So as of now, these are the four major points on which BERT differs from transformer. So let's talk about the structure of BERT, how it differs from transformers in that case. So in case of a BERT base, so BERT also have different variants. So we'll be discussing about BERT base and BERT large. So in BERT base, we have multi heads equals to 12. So if you remember in transformers in the original paper, we have 8 multi heads, but in case of BERT, we have 12 multi heads. Also, the embedding dimension has been increased, that is 784 from 512. Also, as if you remember in transformers, the repeated number of blocks in encoder and decoder, if you remember that 4 layers that we're repeating again and again in encoder was 6. Now we are repeating this entire block for 12 times. This is called as BERT base. Now in case of BERT large, the multi heads is increased to 16, the embedding size of 124, and the number of blocks that are repeated is 24. I guess you need to go back and check out my transformers video to get a better understanding. So here's a base architecture that you can visualize how BERT looks like. So if you remember, you must have remember these 4 layers that we have discussed already. Multi-head attention, add a norm, feed forward, add a norm. So if you haven't, you can check out my previous videos. Now this forms our one code block, encoder 1. Similarly, encoder 2, encoder 3, encoder n, and eventually we get our output. This is a repeated block that we are talking about. So uh, now we will be discussing about how a BERT model is trained. So the training of BERT is divided into two parts. One is pre-training and other is fine-tuning. So the role of pre-training is to understand the language model on which dataset that the model is getting trained on. And fine-tuning refers to all the later on tasks that you can do using the language model. So for example, if you wish to generate a question answer system, you wish to generate text to text speech. So first of all, what you would be doing is you will take a pre-trained BERT model that understands the language in which you are working, and eventually you will do the fine tuning for that. Because like for example, like for understanding a language model, you need some heavy weight lifting. You need to train the model for longer length on a big data set, and this can't be possible again and again. So like in case of transformers, the bigger limitation was this only key. For any problem that we are facing, like for any problem that we need to solve, we are training the model from scratch. But in case of BERT, we won't be doing that. We will be pre-training the model once and then fine-tuning it every time we wish to solve a certain problem. So let's understand how pre-training works. So first of all, let's understand how the embedding that are getting fed into this encoder of BERT is prepared for pre-training. So this encoding, so if you remember in transformers, what we were doing is that we were generating an input embedding and then adding the positional encoding into that particular vector. Now in case of pre-training, we are adding a few more things. So first of all, the text sequence that would be used for training is broken into tokens using word piece tokenizer. So I will be discussing this separately in in some of my other videos. Secondly, what happens is that in case of the sequence that has been fed, we will be adding some new tokens into that. That is CLS and SEP. So what is the use of these tokens? CLS is added in the beginning of the sentence, as you can see in the example. Assume that we have this particular sequence. He is a good boy. He is a star footballer in a single input. So in this case, we will be adding CLS in the beginning and SEP after the end of every sentence. So as you can see, it has two sentences. So we have SEP at two places and CLS at one place. Similarly, they have been together. In this example, also we have just one SEP because there is just one sentence in the entire input. The second the second addition that we are doing is a segment embedding that is getting added. So what happens is that in the input you can see that we have multiple sentences coming in. These sentences can be taken as multiple segments of the input. So for each segment, we are representing mathematically by putting some value a for all the tokens representing the first segment, b for all the tokens present in the second segment. This is how a segment embedding is generated. So what we're doing is that for multiple sentences, so the tokens in a particular sentence should have the same value in the segment embedding. So this was an example for he's a good boy, he's a star footballer, a b. Similarly, if we have three sentences, it would be a b c c c. So just to represent key, these are different sentences. Now the final token embedding that gets fed into the encoder structure, encoder that encoder one would be a summation of token embedding that is generated to the input embedding layer, if you remember in transformer, similar to that. Second would be segment embedding getting added, and third would be the positional embedding getting added. So I have already discussed positional embedding in my previous videos. You can check that out. What is it? So for this particular sentence, if we have a sentence, Paris is a beautiful city, I love Paris. So first of all, we will be adding some new tokens, CLS, SEP, SEP. Then we'll be generating token embeddings for them. Now this can be done using anything, word to vec or some easier method. You can check out my previous video how we have done this for transformers. Segment embedding is generated for this sentence, and positional embedding is generated for this sentence. Now, in pre-training, we will be training the model in two ways on two problems. That is masked language modeling, that is MLM, and second is next sequence prediction. So let's understand what are these two problems on which the pre-training part is based out of. Now we will be understanding what is masked language modeling. That is the first problem statement in pre-training part. So let's first of all understand how the training data set is prepared. So the entire idea of masked language modeling is that we would be masking out a few tokens randomly in the input sentences. So as you can see that uh, I am masked boy. I am a smart boy. So the word smart can be masked. She loved masked with chocolate masked. That means these tokens are getting masked randomly. The entire idea of masked language modeling is that we would be masking out some random tokens, and eventually we would be training the model to determine these masked tokens. So if we feed in this particular sentence, what the model should be able to predict probabilities for this particular masked tokens in that. So in the entire data set, for 80% of the data, we would be masking out random tokens in the sentences. For the remaining 10%, we would be replacing certain tokens with random tokens. He is cake best friend. He is my best friend, so my is replaced by cake. Bus love each other. They love each other, so we are replacing they with bus. So this can be random tokens getting replaced, and no alteration in the remaining 10%. He's my best friend. They love each other. So the model can get three types of inputs. Having one token mask at any position, 80% of 80% of the input would be something like that. 10% of the cases we would be replacing certain tokens with random tokens, as you can see bus love each other, and he's my cake best friend, etc. And no change in the remaining 10% of the input data. Now a question comes in ki, what is the significance of masked language modeling? So remember in the point where we were discussing that BERT is a bidirectional training model, and transformers are not. So why is it so? So this is because of masked language modeling. So if you notice, in case of transformers, what we were doing is that we were trying to predict the next token given the previous tokens. So it was unidirectional. You don't have information from the from the future. So, but in case of BERT, what we are doing is that we are training the model with masking certain tokens randomly. So in that case, we also know which tokens are present ahead of the token and which tokens are present behind that token. In this case, the model is able to learn from both the directions. But in case of a transformer, which is a unidirectional training model, we mask out the future tokens that the model hasn't seen. If you remember, masked multi-head attention definition that we discussed in my last video. So in that case, if we are at a position 3 in predicting certain sequence, so the model is not able to see fourth, fifth, sixth, seventh tokens that are present in the future. But in case of BERT, as you know, we are masking out random tokens. So the model is provided this information from the future tokens as well. What are the tokens present ahead of it, and what are the tokens present behind of it, and this helps us in bidirectional training of the model. Also, there can be a question that why do we need three different types of input, like mass, random, like we are masking certain sentences, we are replacing random tokens, and in some of them we are not changing anything. As I told you, that BERT, in BERT, the pre-training part is majorly to understand the language model, right? But eventually we would be fine-tuning it as well. What will happen is that if we would train the entire model just on masking certain tokens, the model will certainly bias on certain problems, and it might not be able to perform pretty well on certain particular tasks. So like in certain tasks we won't be having any masking happening. So in that case, the model may overfit on if we just provide with mask tokens for 100% of the data set. That is why we are bringing out some sort of a randomness in the data set so that the model doesn't overfit on mass language modeling problem only. So let's understand the MLM model structure. Most of the things are pretty easy. We are not doing much of the things. So eventually the core BERT remains the same. Assume that we are trying to predict for Paris is a beautiful mask. I love Paris. So we need to predict for mask. This is the input that we are giving. It goes into this BERT architecture. If you remember, I told you in BERT large we have 12 encoder. In BERT BERT we have multiple encoder blocks, that four layers that we repeat every time. Here we are. So encoder 1, encoder 2, encoder 3 represent those particular blocks. Now once it passes through BERT, we get certain sort of embeddings for each of the token that we have. Now we know what is the position for the mask token. Eventually we will apply softmax plus FNN, feed forward network FFN, to get the probability for all the possible tokens. So here you can see that. So once we have applied BERT, we are applying two more layers. Softmax, we are applying activation function softmax plus feed forward network, and eventually we are getting probability for the most apt token that should replace the masking. So if we run through the example, the input is Paris is a beautiful city. I love Paris taken as an input. The input text sequence is tokenized using word piece. So we have tokenized this sequence. The next step would be city is masked and CLS and SEP tokens are added. So as you can see, city is masked in the example, and CLS and SEP tokens are added. The three embeddings token, positional, and segment embeddings are generated and added together. This merged embedding is fed to BERT base, if you remember, where we have 12 code blocks getting repeated. So in case of transformers, we have just 6. In case of BERT base, we have 12. A tension vector is generated for each token, and embedding for the mask token that has been generated, that is used to determine what should be the apt word for here. Next part in the pre-training of BERT is next sequence prediction. So as I told you earlier, in pre-training, we would be training the model on two major problems, that is MLM, masked language modeling, and second is next sequence prediction. So let's understand what is next sequence prediction. So assume that we have three sentences. He is handsome, the sun rises in the east, and his name is Raman. Now, if we form two input sequences using the above sentences, he is handsome, his name is Raman, the sun rises in the east, his name is Raman. Now, in case of next sequence prediction, what we're trying to check is whether the second sentence in a particular input is associated with the first sentence or not. So, in case of first one, he is handsome, his name is Raman. This is associated. In this case, the second sentence is associated with the first one, but in case of the second sentence in case of the second input, the second sentence is not associated with the first sentence. So for the first one, the label would be yes. Yes, the second sentence is associated with the first one. But in case of the second input, the label would be no. So in case of next sequence prediction, what we are doing actually is that we are trying to figure out, we're trying to make the model understand, in case of multiple sentences coming in the input, whether the second sentence is associated with the first one or not, or vice versa. Now, how to prepare the training data set for next sequence prediction? So it's pretty easy. We would pick out a particular document, any document we can pick out. Now we would be placing two consecutive sentences together from the document and label them as yes, and then pick up two random sentences from the same from the same document or from other documents as you wish, and then label them as random, label them as a zero. So join two consecutive sentences from either document and mark as yes. Take two random sentences, each from two documents, and mark as no. So this can be like, I guess you must have got an idea how we are trying to prepare the training data set. If you are able to pick out two consecutive sentences from any random document, the label would be one. Else, then we would be picking out random sentences from different documents or even from the same document. And the same document can be an issue. So because we might find some association, so it would be better to take sentences from different documents and mark them as no. Now, the embedding that we're generating is pretty easy. It's pretty similar to what we discussed in MLM. Also, we would be adding the CLS and SEP tokens as we discussed in case of MLM. Now, let's understand the architecture, how it is changing a bit. So, again, assume that we are inputting the sentence, she cooked pasta. It was delicious. Now, it again goes to the BERT base model that comprises of 12 code blocks. After that, once we get the attention vector for each of the input token, we would be taking the embedding for the first token, that is CLS token, and we'll be applying a softmax plus feed forward network to get for the binary classification whether the second sentence was no next or is next. So as you can see that the probability for is next is 0.9, hence she cooked pasta, it was delicious. So it was delicious was associated with the first sentence. So if you remember, in case of MLM, what we are doing is that we are applying the softmax plus feed forward network on the masked tokens embedding. Now in case of NSP, we are applying this softmax plus feed forward to the first token, that is the CLS token. So it's the CLS token that is helping us to determine whether uh, the sentence that the second sentence in the input is associated with the first sentence or not. So, going back why we were adding segment embedding and extra tokens does make sense now, because CLS token is helping us out in the NSP problem. Also, the segment embedding that we were adding AAA, BBB, CCC is also making sense, because now we understand why we need to differentiate the different sentences present in the input. Also, the separator token also helps us in determining when the new sentence starts. Right. Now moving on to the last part, that is fine tuning a BERT. So fine tuning is nothing but we would be adding a few layers over the top of the trained BERT model that we did in pre-tune in the pre-training part, and eventually doing the problem solve. We will be solving out a problem that we wish to solve, be it text classification, or it can be anything. It can be sequence or sequence prediction. It can be anything. So we'll be using the BERT base as the core, and eventually adding out a few layers over that. So as you can see, add out an FNN over BERT, feed CLS token output embedding to FNN, depending upon what is the. So if you are going for some text classification, you can take out the CLS token. Else, if you are going for sequence prediction or you're going for some mass language modeling also, any problem statement that you wish to solve using this model, it can be solved by adding some certain layers on the top of it, depending upon the problem statement. So, just a last question. So, is the fine tuning task training similar to what we did in pre training? A big no. In pre training, what we did is that we have trained the entire BERT model. So, in case of fine tuning, we won't be doing that again. So, we would be freezing out the BERT model that we are using, and we'd be training just the added layers that we are going to add on the top of this BERT, and the rest of the layers present in the BERT won't be trained again. So that is why the training becomes a lot faster, and we are able to solve our problem a lot earlier, for which we were earlier we were trying to train the entire model again and again. So as you can see the architecture, I love Paris. Assume that it is a classification problem. I love Paris. We have a pre-trained model. It generates the attention embeddings for each of the token. Then we're applying a softmax plus feed forward network and giving us the classification.